There is an orbit around the Moon that NASA discovered in 1968, mapped with extraordinary precision, and then quietly never used again. Not because it was dangerous, not because it was impractical, but because what they found there was so strange, so difficult to explain, that the agency essentially decided to look away for more than half a century. And now, after 55 years of deliberate avoidance, that orbit is back at the center of some of the most important space missions humanity has ever attempted. And when you understand why it was abandoned in the first place, you will understand something about the Moon that almost nobody on Earth actually knows. If this kind of deep dive into the hidden history of space exploration is something you want more of, hit that subscribe button right now, because we go places most channels are too afraid to follow. So let us start at the beginning. Not the dramatic beginning where astronauts are floating around in lunar orbit. Let us start earlier than that. Let us start with the Moon itself, because almost everything you think you know about it is built on assumptions that turned out to be wrong. The Moon is supposed to be simple. That is the impression most of us grew up with. It is a dead rock. It has no atmosphere. It has no magnetic field to speak of. It has no geological activity. It just sits there, locked in its orbit, showing us the same face forever because of something called tidal locking. It is the most studied object in the night sky. We have sent missions there. We have walked on it. We have driven rovers across its surface. And yet, hiding inside this supposedly simple, dead, boring rock is one of the strangest gravitational anomalies ever documented in the history of spaceflight. And the story of how we found it, what it means, and why we spent 55 years pretending it barely existed is one of the most fascinating and underappreciated stories in all of science. Let us talk about gravity for a moment, because this whole story hinges on gravity behaving in ways it absolutely should not behave. When you are orbiting a perfectly uniform sphere, your orbit is stable and predictable. Every time you come around, you are at the same altitude, moving at the same speed, following the same path. The math is clean. The physics is clean. This is called a Keplerian orbit, named after the astronomer Johannes Kepler, who figured out the fundamental rules of orbital mechanics back in the early 1600s. Those rules work. They are reliable. They have been used to navigate spacecraft across billions of kilometers of empty space with extraordinary precision. The problem is that the Moon is not a perfectly uniform sphere. Nobody really expected it to be perfectly uniform. No planetary body is perfectly uniform. Earth certainly is not. Earth has mountain ranges and ocean trenches and a slightly flattened shape at the poles that creates very mild gravitational variations. But those variations are gentle, gradual, and well understood. Engineers who design satellite orbits around Earth know exactly how to account for them. It is routine. It is engineering. It is not a mystery. What NASA found at the Moon in 1968 was not routine, not gentle, and not at all easy to explain. It started with the Lunar Orbiter program. Before any human being could land on the Moon, NASA needed to know exactly what they were landing on. They needed high-resolution maps of the surface, and they needed precise measurements of the gravitational field. So between 1966 and 1967, NASA launched 5 robotic spacecraft called lunar orbiters. These were not glamorous missions. They did not make headlines the way the Apollo flights did, but they were absolutely critical to the success of everything that came after them. The lunar orbiters flew around the Moon at low altitudes, photographing the surface in extraordinary detail and transmitting data back to Earth. And almost immediately, the navigators who were tracking these spacecraft noticed something wrong. The orbits were not behaving the way they should. Every time a lunar orbiter passed over certain specific regions of the Moon's surface, its orbit would shift slightly. It would speed up, or it would drift inward, or it would change in some subtle but measurable way. And when the spacecraft came back around on its next orbit, the shift would happen again, in the same place, with the same effect. Whatever was causing this was not random. It was not noise in the data. It was a real and repeatable gravitational effect tied to specific geographic locations on the lunar surface. The scientists and engineers who noticed this had a name ready for whatever was causing it. They called them mascons, short for mass concentrations. Now the concept of a mascon is not inherently mysterious. The basic idea is simple. If there is a region of the moon where the density of material is higher than the average density of the surrounding rock, that region will have slightly stronger gravity. When a spacecraft flies over it, that extra gravitational pull will tug on the spacecraft in ways that deviate slightly from the predicted path. Find enough of these regions, map their locations and strengths precisely enough, and you can account for their effects. You can build them into your navigation models. You can predict exactly what your spacecraft is going to do. Problem solved. Except when NASA actually dug into the data from the lunar orbiters, what they found was not a simple engineering problem with a clean solution. What they found was something that raised far more questions than it answered, because the mascons they discovered were enormous, vastly larger and more powerful than anything they had expected to find. And they were located in very specific places that made their existence deeply puzzling. The mascons were sitting under the large circular basins on the near side of the moon, the ones with names like Mare Imbrium, Mare Serenitatis, Mare Crisium, and Oceanus Procellarum. These are the dark patches you can see on the moon with your naked eye on a clear night. The ancient astronomers who named them thought they might be seas, which is what the Latin word mare means. We now know they are not seas of water. They are vast plains of solidified lava rock, formed billions of years ago when enormous volcanic eruptions flooded the interior of ancient impact craters. And sitting directly beneath these dark volcanic plains were these massive, dense concentrations of material, creating gravitational anomalies strong enough to visibly perturb the orbits of spacecraft flying overhead. But here is where it gets strange, because a mascon under a volcanic plain should not exist, at least not the way these ones do. Think about how lava works. When a volcano erupts, it sends up molten rock from deep inside the planet. That molten rock flows outward, filling in lower areas. Then it cools and solidifies. The resulting rock is dense, yes, but it is not dramatically denser than the surrounding material it flowed over. You would expect some gravitational variation, but nothing dramatic. Nothing strong enough to throw off a spacecraft's orbit. And yet, the mascons beneath the lunar mare were throwing off spacecraft orbits in a very significant way. The concentrations of mass down there were far greater than you could explain simply by piling volcanic rock on top of the surface. So the question became, what is actually down there? One leading theory held that the mascons were not created by the volcanic activity itself, but by what caused the volcanic activity in the first place. The large circular basins on the moon's near side are ancient impact craters. Enormous craters, formed billions of years ago when asteroids and other large bodies slammed into the young moon with tremendous force. The theory goes like this. When a giant impactor hits the moon, the collision is so violent that it vaporizes the impactor and a large amount of the lunar surface rock. The explosion carves out a deep basin in the crust. But then something interesting happens. The crust around that basin, suddenly relieved of the weight of all that rock that just got blasted away, begins to rebound. It is like pressing a dent into a rubber ball and then letting go. The crust springs back upward in the center of the impact zone, and as it does, it pulls dense material from deep in the moon's interior up toward the surface. Meanwhile, the basin fills with lava from volcanic eruptions triggered by the heat of the impact. So what you end up with is not just a pond of solidified lava sitting on top of normal rock. You have a situation where the crust was fundamentally disrupted, where deep and unusually dense material was pulled upward, and where layer upon layer of volcanic rock then piled on top of all of that over millions of years. The result is a region of the moon where the average density of the material from the surface all the way down to significant depth is dramatically higher than the surrounding highlands, and that high-density region creates a powerful gravitational anomaly. This explanation made sense. It was a good working model. Scientists published papers about it. The mascons became an accepted feature of lunar science, and everyone more or less moved on. But moving on was easier said than done for the engineers, who actually had to fly spacecraft around the moon. Because what the lunar orbiter data had revealed was that the moon's gravitational field was not just lumpy in a manageable way, it was lumpy in a way that made low lunar orbit genuinely chaotic. If you tried to maintain a circular orbit at low altitude over the moon's near side, Without constant engine burns to correct your path, the Maskons would gradually distort that orbit in increasingly severe ways. A spacecraft that started in a nice, clean, circular orbit could, over the course of weeks or months, have its orbit warped to the point where it dipped dangerously low at certain points, low enough to potentially crash into a mountain range or the rim of a crater. NASA discovered this the hard way. Several of the Lunar Orbiter spacecraft, which were simply left in their orbits after their mapping missions were complete, eventually impacted the lunar surface, not because anyone directed them to do so intentionally, because the gravitational perturbations from the Maskons gradually warped their orbits until the spacecraft hit the moon. This was actually used strategically in some cases. Engineers could predict where and when the spacecraft would crash, and by using that crash as a seismic event, they could learn something about the interior structure of the moon. But the broader lesson was clear. Low lunar orbit was not stable. If you put something there and walked away, the moon's gravity would eventually reach up and drag it down. This created a profound engineering challenge for the Apollo program. The astronauts who landed on the moon needed a command module to stay in orbit overhead, while the lunar module descended to the surface and then came back up to rendezvous. The command module pilot would be alone up there, flying in circles around the moon, for as long as it took the surface crew to complete their mission. That could be days. And you absolutely could not have the command module's orbit degrading dangerously, while Michael Collins or Ken Mattingly or Al Worden was sitting up there waiting. So NASA's mission planners had to think very carefully about orbital altitude. The higher you fly, the weaker the influence of the Maskons becomes. The gravitational anomalies are concentrated near the surface. Get far enough away, and their effect becomes negligible. But there is a trade-off. The higher you fly, the more fuel it takes to get down to the surface and back up again. Every kilometer of extra altitude is weight and propellant that you have to carry all the way from Earth. And on Apollo, where the weight of every component was calculated down to fractions of a kilogram, that trade-off mattered enormously. The Apollo command modules orbited at altitudes ranging from about 60 to 110 kilometers above the lunar surface. At those altitudes, the Maskons could still perturb the orbit, but the effect was slow enough that it was manageable over the few days of a typical mission. Mission controllers on the ground tracked the command module's orbit continuously and could instruct the astronauts to fire the engine occasionally to correct any drift. It was not elegant, but it worked, and the program was focused on the near-term goal of landing astronauts safely and bringing them home. The deeper question of why the moon's gravity was so weird was left for scientists to puzzle over later. But there was another orbit that NASA had identified. An orbit that the data suggested was genuinely, mathematically special. An orbit where the gravitational perturbations from all those Maskons, rather than accumulating and building up over time into something dangerous, would actually balance each other out. Where a spacecraft could, in theory, fly around the moon essentially forever without needing engine burns to maintain its altitude. A stable orbit around a body as gravitationally chaotic as the near-side moon was something that should not exist by any conventional understanding of orbital mechanics. And yet the mathematics said it did exist. The concept of a frozen orbit around the moon became one of the most intriguing theoretical topics in astrodynamics. The term frozen orbit refers to any orbit where the perturbations from a non-uniform gravitational field cancel each other out in such a way that the orbit maintains its shape and orientation over very long periods of time. The orbit is not truly static. The spacecraft is still being tugged and pushed by all those irregular mass concentrations. But the net effect over each complete orbital cycle is essentially zero. The spacecraft ends up back in almost exactly the same position it started, time after time, without any corrective burns needed. For Earth-orbiting satellites, frozen orbits are a known and useful concept. Weather satellites and Earth observation spacecraft are sometimes placed in frozen orbits to maintain consistent coverage of specific regions without needing constant station-keeping maneuvers. The math is well understood. The orbits are routinely used. For the Moon, the situation was far more complicated. Because the Moon's gravitational field is so much more irregular than Earth's, and because the perturbations from the Maskons are so strong relative to the average gravity, finding a frozen orbit that actually works requires navigating a much more complex mathematical landscape. For most altitudes and most inclinations, no stable frozen orbit exists. The perturbations are just too strong and too unbalanced. But at one very specific combination of altitude and orbital inclination, something remarkable happens. The altitude is approximately 27 kilometers above the lunar surface. This is extremely low, vanishingly close to the surface by the standards of orbital mechanics. At 27 kilometers, you are skimming the tops of the tallest lunar mountain ranges. You are close enough to the surface that the terrain below you is not a distant abstract thing. It is something you could almost reach out and touch. At this altitude, the perturbations from individual mascons are at their strongest, but they are also, in a very precise mathematical sense, at their most balanced. The gravitational tugs from the various mass concentrations at this specific altitude happen to counteract each other in such a way that a spacecraft placed there can maintain its orbit with extraordinary stability. The orbital inclination that produces this effect sits at specific angles that essentially thread the spacecraft's path between the gravitational influences of the various mascon regions in just the right way to maintain the orbit's stability over time. Get the combination of altitude and inclination right, and you have a frozen orbit around the moon. Get it wrong, and you get a gradually destabilizing orbit that eventually ends in a crash. When NASA's astrodynamicists identified this orbit in the late 1960s and early 1970s, the reaction was not straightforward excitement. Because while the frozen orbit was theoretically elegant, it also raised a question that nobody had a good answer to. Why does this orbit exist? The gravitational field that makes this frozen orbit possible is itself the product of all those mascons. And the mascons are products of the specific pattern of giant impacts the moon experienced billions of years ago. The moon is covered in craters of all sizes, the result of billions of years of bombardment from space. But the specific large basins on the near side, the ones where the mascons are strongest, are arranged in a particular geographic pattern. And it is precisely that geographic pattern which creates the specific gravitational landscape that, at exactly the right altitude, produces the frozen orbit. Now, the moon has two sides that are radically different from each other. This is one of the strangest things about our nearest neighbor, and something that is still not fully explained. The near side, the face that always points toward Earth, is dominated by the large dark Maria, those volcanic plains sitting on top of the mascon regions. The far side is almost entirely covered in rugged, heavily cratered highland terrain. The crust on the far side is significantly thicker than the crust on the near side. The distribution of large impact basins is dramatically different, and the gravitational field on the far side, while certainly not uniform, is nowhere near as strongly perturbed as it is on the near side. Why are the two sides so different? This is one of the fundamental unsolved questions of planetary science. The leading hypothesis involves the early history of the solar system, when the moon first formed, most likely from the debris thrown off by a giant impact between the early Earth and another planet-sized body. It was covered by a global magma ocean, a world of liquid rock. As that magma ocean cooled over tens of millions of years, different minerals crystallized out of it at different temperatures and sank or floated accordingly. Lighter minerals rose to form the crust, while denser minerals sank toward the interior. But this cooling process was not symmetric. The near side of the moon, even in those early days, faced a hotter early Earth. The far side faced the cold of open space. The difference in cooling rates led to differences in crustal thickness, which led to different patterns of volcanic activity and impact basin formation, which led ultimately to the radically different terrain we see on the two sides today. The frozen orbit that NASA identified is a product of the near side's gravitational peculiarities. It is, in a strange sense, a mathematical fossil of the early solar system's history, a feature baked into the moon's gravitational field by events that happened billions of years ago and only discoverable by spacecraft capable of measuring gravitational variations with extraordinary precision. But then why did NASA avoid it? This is where the story becomes genuinely strange, because the reasons for avoiding this specific orbit for 55 years are not all obvious. There is the straightforward engineering reason, which is that a 27-kilometer orbit is a very low orbit, and in the early days of the space program, flying that close to the surface raised legitimate safety concerns. If your spacecraft's engine failed at that altitude, you would have almost no time to respond before you impacted the surface. The margin for error was essentially zero. There is also the question of what you would actually do in a frozen orbit around the moon. If you are using the moon primarily as a destination for crewed surface missions, you want your orbital operations at a more comfortable altitude. You want time to troubleshoot if something goes wrong. You want margin. The frozen orbit at 27 kilometers is extremely useful for certain types of observation and scientific measurement, but it is not a comfortable place to operate crewed spacecraft by 1970s standards. But there is another layer to this story that is more subtle and more interesting. After Apollo ended, NASA's attention shifted away from the moon almost entirely. The space shuttle, space stations, and then the push toward Mars dominated planning and resources. The moon became a place we had been, not a place we were actively studying. The detailed astrodynamical questions about lunar frozen orbits became topics for academic papers rather than mission planning documents. The specific knowledge of that orbit existed in the literature, but it was not being actively developed or tested. And then there was the data problem. The lunar orbiters had mapped the near-side gravitational field with reasonable precision, but the far side, the side of the moon that never faces Earth, the side where you cannot maintain radio contact from Earth, that side was almost completely uncharacterized in terms of its gravitational field. And any mission that involved orbiting the moon, particularly a low orbit, needed to have a complete gravitational model of the entire body, not just the half you can see. Think about what this means for a moment. The far side of the moon is essentially inaccessible to direct radio communication from Earth. Any spacecraft on the far side is out of contact. The Chinese mission Chang'e 4, which landed on the far side in 2019, had to use a relay satellite positioned at a special point in space called the Earth-Moon Lagrange Point 2, a location where the satellite could see both the far side of the moon and the Earth at the same time. Without that relay, there is simply no way to communicate. And without communication, you cannot track the spacecraft's exact position precisely enough to build a detailed gravitational map. For decades, this meant that the far side gravitational field remained poorly characterized, and a poorly characterized gravitational field means you cannot reliably predict what your spacecraft's orbit is going to do. For a high-altitude orbit, this matters less. But for a low orbit, like the frozen orbit at 27 kilometers, where the gravitational perturbations are strongest and the consequences of an unexpected deviation are most severe, not knowing the complete gravitational field is a potentially mission-ending problem. You could do all the math correctly for the near-side gravity and find that when your spacecraft swings around to the far side, something unexpected happens that your model did not predict. And by the time your spacecraft comes back into view from Earth, it has already impacted the surface. This is not a hypothetical concern. Spacecraft have been lost for exactly this kind of reason. When your gravitational model is incomplete, your orbit predictions are incomplete. When your orbit predictions are incomplete, spacecraft fly into mountains. The moon has plenty of mountains, so the frozen orbit sat there in the mathematical literature, interesting and theoretically beautiful, while the practical barriers to actually using it safely remained firmly in place. Then something changed. In 2011 and 2012, NASA launched a mission called GRAIL. The name stands for Gravity Recovery and Interior Laboratory. It was, in many ways, the mission that the Lunar Orbiter program had been pointing toward for 40 years. GRAIL consisted of 2 spacecraft flying in close formation around the moon, not just flying around and measuring their position, but measuring the incredibly precise distance between the 2 spacecraft as they flew, because as the spacecraft passed over regions of stronger or weaker gravity, they would accelerate or decelerate slightly relative to each other. By measuring those tiny changes in separation with extraordinary precision, the mission could build a complete, detailed map of the moon's gravitational field, near side and far side, high resolution, full coverage. The results from GRAIL were astonishing. The gravitational map that GRAIL produced revealed that the moon's interior is far more complex than anyone had realized. The mascons on the near side were mapped in extraordinary detail, confirming and greatly refining everything that had been inferred from the lunar orbiter data decades earlier. But the far side was full of surprises. The gravitational field there was not as smooth and featureless as the relatively uniform highland terrain might have suggested. There were anomalies on the far side too, different in character from the mascons on the near side, but real and significant nonetheless. And with this complete gravitational map in hand, astrodynamicists could now revisit the question of the frozen orbit with the full picture for the first time. What they found was that the frozen orbit at 27 kilometers was real. The mathematics had been right all along, but Grayle's data allowed them to refine the exact parameters with a precision that had never been possible before. The precise altitude, the precise inclination, the precise orientation of the orbital plane that produced maximum stability. And the refined answer confirmed something extraordinary. A spacecraft placed in this orbit would maintain its altitude with far greater stability than any other low lunar orbit. Not perfectly stable, nothing is perfectly stable in the real universe, but stable enough to be genuinely remarkable, stable enough to be useful. Now here is where the story connects to everything happening in space exploration right now. Because NASA is going back to the moon. Not just for brief visits this time. The Artemis program is designed to establish a sustained human presence in the lunar system. This means not just landing astronauts on the surface, but building infrastructure. A space station in lunar orbit called the Lunar Gateway, a permanent presence. Regular missions, operations that will continue for years, not days. And for sustained operations around the moon, the frozen orbit is suddenly not an obscure theoretical curiosity. It is a potentially critical operational resource. Think about what you could do with a spacecraft in a stable, low orbit around the moon that does not require constant fuel expenditure to maintain its altitude. A satellite in that orbit could provide continuous coverage of specific regions of the lunar surface. It could serve as a communications relay for surface crews. It could conduct detailed scientific observations of the surface geology and mineralogy. It could monitor the behavior of the lunar environment over long time periods, all without burning through its propellant reserves just to stay in orbit. Propellant is the critical resource for any space mission. Every kilogram of propellant you have to carry to a spacecraft in lunar orbit is a kilogram that had to be launched from Earth at enormous cost, or eventually, someday, delivered from some other source in the solar system. A spacecraft that can maintain its orbit without burning propellant is a spacecraft that can stay operational longer, carry more scientific instruments, and do more useful work. For a sustained lunar infrastructure program, that matters enormously. The potential applications that engineers and mission planners have started seriously discussing are genuinely exciting. A communications satellite in the frozen orbit could maintain line-of-sight contact with surface crews in a way that a higher orbiting satellite simply cannot, because from 27 kilometers up, you have an extraordinarily close and detailed view of the surface. A scientific observatory in that orbit could map the surface mineralogy with a resolution that would reveal details about the distribution of water ice and other volatile materials that could be critical resources for a permanent human presence. A technology demonstration mission in that orbit could serve as a testbed for the autonomous systems that future lunar operations will depend on. And there is another factor that has fundamentally changed the calculation. The Grail gravitational map is good, but it can be made even better. One of the effects of actually operating spacecraft in low lunar orbit is that you learn more about the gravitational field from their behavior. Every time a spacecraft deviates slightly from its predicted path, that deviation contains information about the gravitational anomaly that caused it. Operate enough spacecraft in low lunar orbit, track them precisely enough, and you refine the gravitational model further. The model becomes more accurate. The orbit predictions become more reliable. The frozen orbit becomes easier and safer to use. It is a virtuous cycle. The more you use it, the better you understand it. The better you understand it, the more confidently you can use it. NASA's Lunar Reconnaissance Orbiter, which has been operating since 2009, has been gradually contributing to this improved understanding. The LRO has operated at varying altitudes during its mission, and tracking its orbit has refined the gravitational model in ways that build on Grail's results. Commercial missions are adding to the picture as well. The burst of commercial lunar activity driven by programs like NASA's Commercial Lunar Payload Services Initiative means more spacecraft are flying to the moon more often, and each one contributes data. The cumulative effect of all this activity is that the gravitational landscape of the moon is becoming understood at a level of detail that simply did not exist when the frozen orbit was first theoretically identified. The barriers to using it safely are coming down, not all at once, not instantly, but steadily and surely. But let us pull back from the engineering for a moment and think about what this story really means, because there is a deeper significance here that goes beyond mission planning and orbital mechanics. In 1968, human beings were about to land on the moon for the first time. The entire weight of the space race, the geopolitical competition between the superpowers, the romantic dream of human destiny among the stars, all of it was focused on that singular achievement: getting there, landing, coming home safely. In that context, a subtle mathematical property of lunar orbital mechanics was background noise. Interesting to the specialists, yes, but not the main event. The main event was Apollo 11. The main event was Neil Armstrong and Buzz Aldrin standing on the Sea of Tranquility, while the entire world watched in astonishment. And that was right. It was the correct priority. The achievement of landing humans on the moon was one of the greatest things our species has ever done. But in the rush to accomplish that achievement, certain threads of knowledge got set aside. Certain discoveries got made and then filed away. The frozen orbit was one of them, a mathematical fact about the moon that was noted, documented, and then essentially ignored for more than half a century, while the world's attention moved elsewhere. And now we are coming back to it not as a curiosity, but as a necessity, because the next chapter of human activity at the moon is not about brief heroic visits. It is about staying, and staying requires understanding the moon with a depth and a completeness that the Apollo era never needed. There is something almost poetic about this. The frozen orbit was created by the moon's own ancient history, by the pattern of giant impacts that scarred the near side billions of years ago, by the volcanic flooding that followed those impacts, by the specific arrangement of mass concentrations that resulted from those events. A gravitational fingerprint laid down in the deep past, discovered by human technology in 1968, ignored for 55 years, and now being recognized as a key to humanity's future presence in the Earth-Moon system. The moon left us a gift in its gravity field, and we only just figured out how to unwrap it. Now let us go a little deeper into the science of mascons, because even the basic question of what they are made of turns out to be more complicated and more interesting than the simple explanation suggests. We talked about how the leading theory connects mascons to giant ancient impacts that brought dense material up from the moon's interior. But the details of that process are still being worked out. One of the things that Grail revealed is that the mascons are not just dense blobs sitting in the middle of the circular basins. The gravitational structure around each mascon is more complex than that. There is a ring of slightly lower than average gravity surrounding the central high-gravity mascon region, and outside that ring there is another zone of slightly elevated gravity. These concentric rings of alternating higher and lower gravity are a direct imprint of the physics of giant impacts. When the impactor hits, the crust does not just create a simple circular crater and stop. The shock wave from the impact spreads outward through the crust, in all directions. As that shock wave moves outward, it creates rings of uplifted and subsided terrain, like ripples spreading from a stone dropped in water but frozen in stone rather than water. Each ring represents a zone where the crust was pushed up or pulled down by the energy of the impact. And because the density of material varies between the uplifted and subsided zones, the gravity varies too. The mascon gravity map is essentially a frozen snapshot of the physics of a collision that happened billions of years ago. What this means for the frozen orbit is subtle but important. The specific gravitational structure of the mascons, not just the central concentration, but all those concentric rings of varying density, contributes to the particular way that the perturbations balance out at 27 kilometers altitude. Change the altitude even slightly, and the balance is disrupted. The concentric ring structure means that at different altitudes, the spacecraft interacts differently with the gravitational complexity of the mascon region. At 27 kilometers, the geometry is just right. The spacecraft's orbital path intersects the gravitational influence of each mascon in a way that, summed over a complete orbit, produces near-zero net perturbation. It is extraordinary, in the literal sense of the word. Ordinarily, this would not happen. The specific physics of giant impacts creating mascons with this specific concentric ring structure, combined with the specific size and rotation rate of the Moon, combined with the specific arrangement of mascon regions on the near side, combined with the specific orbital mechanics of a body at this particular distance from Earth. All of those factors happen to conspire to create a frozen orbit at a very specific altitude. If any one of those factors were different, the frozen orbit might not exist at all. The Moon is, in this respect, a very peculiar place. Its gravitational structure is not just interesting. It is interesting in a way that has direct consequences for how we can operate in and around it. Understanding those consequences took us more than half a century from first discovery to practical application. There is also the question of water, because the story of the Moon in the 21st century is, to a significant degree, the story of water. In the decades following Apollo, the scientific consensus was that the Moon was bone dry. The conditions on the lunar surface, extreme temperature swings, bombardment by solar radiation and micrometeorites, the total absence of any protective atmosphere should destroy any water molecules that land there almost instantly, and the samples brought back by the Apollo astronauts appeared to confirm this. They were extraordinarily dry. The lunar rocks contained almost no water. But then, starting in the 1990s and accelerating rapidly in the 2000s and 2010s, evidence began accumulating that the situation was more complicated. There were hints of water ice in the permanently shadowed regions of the lunar poles, places where sunlight never reaches, where temperatures drop to the lowest in the entire solar system, cold enough that water molecules that found their way there over billions of years through asteroid and comet impacts could be frozen in the regolith, preserved indefinitely. The confirmation came in 2009 when NASA deliberately crashed a spacecraft called L-Cross into a permanently shadowed crater near the South Pole. The impact kicked up a plume of material that was analyzed by a following spacecraft, and the results were clear. There was water ice in the crater floor, significant quantities of it, not just traces, not ambiguous signals, but real, confirmed water ice. Since then, the evidence for lunar water has continued to grow. In 2020, NASA announced that observations from an airborne observatory called SOFIA had detected water on the sunlit surface of the Moon, not just in permanently shadowed craters. On the surface itself, presumably trapped in tiny glass beads created by micrometeorite impacts, and in other microscopic structures that protect the molecules from destruction. And now the question is not whether there is water on the Moon, but how much, where exactly it is, and whether it can be extracted and used. Water is not just important for drinking. Split water into its constituent elements, hydrogen and oxygen, and you have rocket propellant. Finding and using water on the Moon could be the key to making sustained human presence there economically and logistically feasible. Instead of shipping everything from Earth at enormous cost, you mine the Moon's own resources. A spacecraft in the frozen orbit at 27 kilometers is ideally positioned to map the distribution of water ice across the lunar surface at the highest possible resolution. From that altitude, the instruments on board could distinguish between regions of slightly different composition with extraordinary detail. The difference between a square kilometer of regolith that contains 0.5% water by mass and one that contains 2% water by mass is economically significant if you are planning a mining operation. And from 27 kilometers up, in a stable orbit that does not require constant fuel expenditure to maintain, you could map the entire surface with the patience and thoroughness that the mission requires. This is the practical link between the obscure mathematical elegance of the frozen orbit and the concrete near-future plans for human expansion into the solar system. It is not just a theoretical curiosity, it is a tool, and we are finally, 55 years after its discovery, beginning to understand how to use it. But let us also acknowledge what we still do not know, because despite everything we have learned from Grail, from the Lunar Reconnaissance Orbiter, from dozens of other missions and studies and papers, there are still fundamental questions about the moon's interior that remain unanswered. We do not fully understand the structure of the moon's core. We know it has a core, a relatively small iron core compared to Earth's proportionally much larger one. But the details of that core's composition, its size, its state, whether it has an inner solid portion and an outer liquid portion like Earth's, remain subjects of active research and some debate. The seismic instruments placed on the surface by Apollo detected moonquakes, and those seismic signals have been painstakingly analyzed to try to infer the interior structure. But the moon's seismic data is difficult to interpret in the same way Earth's is, partly because the moon's interior damps seismic waves differently than Earth's does, and partly because we simply do not have enough seismometers placed widely enough across the surface to fully triangulate interior structures. We also do not fully understand why the near side and far side are so different. The leading theory involving asymmetric cooling of the early magma ocean is plausible and supported by some evidence, but it does not explain everything. There are details of the difference in the chemical composition of the crust, in the distribution of certain minerals, in the pattern of volcanic activity, that the simple asymmetric cooling model does not cleanly account for. Some researchers have suggested that the early moon might have had not one but two magma oceans at different times. Others have proposed that a secondary impact, perhaps a smaller companion moon merging with the early moon, could have contributed to the asymmetry. None of these alternatives is conclusively supported by current evidence, and none of them is definitively ruled out. What Grail's gravity map tells us is that the difference between the near and far sides goes deep. It is not just a surface feature. The gravitational differences reflect real differences in the distribution of mass all the way through the crust and into the upper mantle. Whatever created the two-sided moon did something profound to its internal structure, not just its surface appearance. And here is the thing about that. Every additional spacecraft we send to the moon, every additional gravitational measurement we take, every moonquake we record with a new generation of seismometers adds to our ability to answer these deep questions. The frozen orbit mission concept is part of a broader picture of increasingly detailed, increasingly sophisticated, increasingly sustained investigation of the moon. We are not just going back to the moon. We are going back to understand it, really understand it, in a way that the Apollo era, focused on the heroic achievement of getting there, never had the time or the tools to do. The moon has been sitting overhead for the entire history of the human species. It has influenced our calendars and our cultures and our myths and our dreams. And for all of that time, we did not know what it actually was. We did not know that its two sides were radically different. We did not know that it harbored massive gravitational anomalies that could throw spacecraft off course. We did not know that there was water ice hiding in its shadowed craters. We did not know that its gravitational field contained a mathematical sweet spot at 27 kilometers altitude where a spacecraft could fly forever without burning fuel. All of that knowledge, every bit of it, has come from spacecraft. From the lunar orbiters and the Apollo astronauts, and the Grail mission, and the Lunar Reconnaissance Orbiter, and the many other missions, American, Soviet, European, Japanese, Chinese, Indian, that have probed the moon from orbit and from the surface over the past 6 decades. And every answer has generated new questions. That is the nature of science. That is what makes this ongoing. We are at a genuinely interesting moment in the history of lunar exploration. The frozen orbit, discovered in 1968, avoided for 55 years, is now being actively considered for operational use. The mascons, detected by the lunar orbiters and mapped in extraordinary detail by Grail, are now being used not just as obstacles to navigate around, but as tools for understanding the deep history of the moon and the early solar system. The water ice, whose existence was debated for decades and confirmed with increasing certainty over the past 20 years, is now at the center of planning for how human beings will live and work on and around the moon in the decades ahead. The questions are not all answered. They may never all be answered, but we are asking smarter questions than we have ever asked before, with better tools than we have ever had before, and with a clearer sense of why the answers matter. The moon is not a simple dead rock. It never was. It is a world with a complex history, a strange internal structure, a gravitational field full of surprises, and a set of resources that may prove critical for the future of human progress.